Так, ну что, давайте проверим, как оно работает. Раз. Есть? Спасибо. Okay, at the previous lecture we proved a version of spectral theorem, namely the functional modal theorem. And because of the importance of this result, let's briefly recall the contents, the statement of the result. So we draw the following picture. Actually, this will be a table. And the table will consist of 2 columns and 2 rows. The columns, the first column will correspond to the structure of star modules over the algebra of continuous functions on a compact Hausdorff topological space X. And the second column will be actually a special case of the first one. It deals with normal operators on the Hilbert space. The first line of the picture gives us functional models in a special case of cyclic star modules and respectively for star cyclic normal operators. And the respective functional modal theorem for cyclic star modules over 0x states that if H is a cyclic star module over 0x, then it is unitarily isomorphic to L2 of x mu for a suitable positive Radon measure on X. So the action of C of x on L2 of x is just pointwise multiplication. So this is the general form of a cyclic star module over C of x. And if we now apply this to normal operators, so let's recall that once we have a normal operator on a Hilbert space H, we may consider H as a star module over the algebra of continuous functions on the spectrum of the operator. Because we have continuous functional calculus, which is a star homomorphism from the algebra of continuous functions on the spectrum to B of H, the continuous functional calculus for our operator. It's a star homomorphism, and so our Hilbert space H becomes a star module over the algebra of continuous functions. So in this special case, we see that if T is a star cyclic normal operator on the Hilbert space H, then it is unitarily equivalent to the multiplication operator, which was denoted by MT. It acts on the big L2 space on the spectrum equipped with a suitable positive Radon measure mu. And the operator MT is just the multiplication by the coordinate. So it acts by the following formula. So this is, briefly, this is the general form of a star cyclic normal operator on the Hilbert space. And the second line gives us functional modal theorems for arbitrary star modules, or respectively for arbitrary normal operators. So if we have a star module over C of x, star module H, then it is unitarily isomorphic to the big L2 over a suitable measure space, omega mu. So omega mu is a measure space. And the module structure on the space is given by a suitable measurable map, which I denote by phi. And to emphasize that this phi determines the module structure, I put it here as a subscript. So phi is a measurable map from omega to x. Measurable map. And the module structure of on L2 of omega over C of x is given by the following formula. So if A is a continuous function on x and f is in L2 of omega, then we compose A and phi, and this will be a bounded measurable function on omega, and just take the pointwise product of A phi and f. So we proved that each star module over C of x is of this form. And in a special case of normal operators, we get the following picture. If T is an arbitrary normal operator on a Hilbert space, then it is unitarily equivalent to the multiplication operator M phi, which acts on the big L2 space, L2 of omega mu. So here phi is a bounded measurable function. And M phi is just the pointwise multiplication by phi. And so this is the general form of a normal operator on a Hilbert space. Okay, so this is our first version of the spectral theorem. It is actually very convenient because this functional model contains almost all essential information, actually all essential information about the operator. So once we... Okay, so today our first goal, actually the main goal, will be to prove another form of spectral theorem, which is stated in terms of the Borel functional calculus. So briefly, the idea will be the following. So we start with a normal operator T on a Hilbert space, a normal operator. We take a compact subset K of the complex plane containing the spectrum. And we already know that there exists a continuous functional calculus for T on K. Continuous functional calculus. Now we consider the bigger algebra, the bigger function algebra, the algebra of bounded Borel functions. We denote it by B of K. Our goal will be to extend the continuous functional calculus to a star homomorphism from B of K to B of H, which satisfies some special properties, which I state explicitly a bit later. And this arrow will be called the Borel functional calculus for T. This is very convenient. Actually, this is much more convenient than the continuous functional calculus, because, for example, we can take here the characteristic function of any Borel subset. And this is a bounded Borel function. Well, after we apply this homomorphism to such a function, we get projection here. And as a result, we will get something like an integral representation. This will be the subject of the next lecture. A kind of integral representation of an arbitrary normal operators in terms of projections. Okay, so this is the rough idea. And now, before we explicitly state this result, let's make a short digression and discuss a useful relation between operators and Cisco linear forms. Well, first of all, we give some definitions. The first definition will be pure algebraic. So suppose we have 3 vector spaces, E1, E2, and F, as usual over the complex numbers. And we say that map, little f, from E1 cross E2 to F is sesquilinear. The Russian for sesquilinear is полуторалинейный. If it is linear in the first variable and antilinear in the second variable, that is, we have the following identities. So f is linear in the first variable and antilinear in the second variable. Here alpha and beta are arbitrary complex numbers. And x, y, and z are elements of the respective spaces. And the special case is a sesquilinear form. Sesquilinear form on E1 cross E2 is just a sesquilinear map to the complex numbers, from E1 cross E2 to the complex numbers. So let's now suppose that our vector spaces are actually normed spaces. Suppose that E1, E2, and F are normed spaces. In this case, we can introduce the notion of a bounded sesquilinear form, or more generally, bounded sesquilinear map. We say that a sesquilinear map F is bounded if there exists a constant, a positive constant and a negative constant C, such that the following inequality holds. So this is very much similar to the notion of a bounded linear operator. And exactly as in the case of bounded linear operators, we have the following simple proposition. Proposition 1. First of all, I claim that f is bounded if and only if it is continuous. And second, I claim that if we consider the space of all, the set of all bounded sesquilinear forms, bounded sesquilinear maps, from E1 cross E2 to F, then this set is actually is a normed space. This is a normed space. More exactly, the norm of a bounded sesquilinear form F is the smallest non-negative constant C satisfying this condition. The smallest non-negative C satisfying this condition. The proof is a simple exercise for you. Actually, the argument is more or less the same as in the case of linear operators. So I hope you remember that a linear operator between normed spaces is bounded if and only if it is continuous. And here, the sesquilinear version of this result is proved in much the same way as for linear operators. And the same concerns the second part of the of the proposition. Okay, let's now consider a special case. Suppose now that we have two inner product spaces, H1 and H2. Inner product spaces. And suppose we have a linear map T from H1 to H2. A linear map. At this point, we are not assuming that T is bounded. T can be any linear map. And we introduce the following notation. We denote by Ft the sesquilinear form on H1 cross H2, given by the following formula. It takes xy to the inner product of tx and y. So it's clear from the construction that Ft is indeed a sesquilinear form. Now the natural question is, when is it bounded? Well, we have the following simple result. Proposition 2. If T is a bounded linear operator from H1 to H2, then the respective sesquilinear form of T is also bounded. And moreover, the norm of this form is equal to the norm of T. So the correspondence between bounded operators and bounded sesquilinear forms is isometric. Well, to prove this result, we just look here at the definition of Ft, apply the Cauchy-Bunyakovsky-Schwarz inequality, and this can be estimated as follows. And if we now look at the definition of a bounded sesquilinear form and at the definition of the norm, we conclude that Ft is indeed bounded. Ft is bounded. And moreover, the norm of Ft is less than or equal to the norm of T. And to prove that actually we have an equality here, we take any x in H1 and look at the norm of T of x. So the square of this norm is actually Ft applied to x and Tx. And so by the definition of the norm of Ft, this is less than or equal to the norm of Ft multiplied by the norm of x and by the norm of T of x. And after we cancel Tx from here and from here, assuming that it is non-zero, we get that we get the following inequality. And this implies that the norm of T is less than or equal to the norm of Ft, and so we have an exact equality here. And this completes the proof. Okay, so in summary, each bounded linear operator determines a bounded sesquilinear form. And it turns out that in the case where H2 is a Hilbert space, so far we didn't assume the completeness. So if we assume that H2 is complete, it turns out that every bounded sesquilinear form comes from a bounded linear operator. I have the following theorem. Suppose that H1 is an arbitrary inner product space and H2 is a Hilbert space. Then the map from the space of bounded linear operators, B of H1, H2, to the space of all bounded Cisco linear forms on the product H1, H2. So this is the map which takes every operator T to the respective form of T. This map is an isometric isomorphism. Well, actually we already know that it is isometric. This follows from proposition 2. Proposition 2 implies that this map is isometric. So to complete the proof, we have to show that it is surjective. We have to show that this map is surjective. This will imply that it is an isometric isomorphism. So to prove the surjectivity, we start with an arbitrary Cisco linear form, F. An arbitrary bounded Cisco linear form on H1 cross H2. And we want to show that F comes from an operator. Well, we do the following trick. We take any element x in H1, and we define a map fx from H2 to the complex numbers by the following simple formula. This will be the complex conjugate of f of xy. Why do I take the complex conjugate here? Well, I do this to get a linear map. So f is cislinear, so it is antilinear in y. But after I take the conjugation here, I get a linear functional. Fx is a linear functional on H2. And moreover, it's easy to see that it is bounded. So this estimate implies that fx is bounded. So it is an element of the dual space, H2 star. And we apply the representation theorem. The representation theorem states that we have a canonical bijection between H2 and H2 dual. So fx comes from a vector, which will be denoted by T of x. There is a unique element T of x in H2 such that fx is given by the inner product with this vector in the following way. Or equivalently, this can be written as follows. After we put the complex conjugation to this equality, we see that f of x, y is the inner product of T of x and y. And here, x is an arbitrary element in H1, and y is a vector in H2. This construction can be performed for any element x in H1. And so we get a map from H1 to H2. We have a map T from H1 to H2. This formula easily implies that T is linear. Actually, this is a little exercise to deduce from this formula that T is linear. And again, by looking at this formula, we see that f is exactly the Cisco linear form corresponding to T. So F equals Ft. And to complete the proof, we have to prove that T is actually bounded. Well, why is it bounded? Again, we take an element x in H1. We look at the norm of T of x. And we recall that the risk representation theorem is actually an isometric correspondence between H2 and H2 star. So the norm of T of x is equal to the norm of Fx. But the norm of Fx can be estimated by using this inequality. So if we look here, we see that the norm of Fx is less than or equal to the norm of F times the norm of x. And that's it. So this inequality implies that T is bounded. So for any bounded cisco linear form F, we have constructed a bounded linear operator T from H1 to H2 such that F equals Ft. This means exactly that our map, this map is surjective. And this completes the proof. So in summary, we have a bijective isometric correspondence between bounded linear operators from H1 to H2 and bounded cisco linear forms. This is quite useful. We will use this result in our proof of the Borel functional calculus theorem, but actually this correspondence has many other interesting applications. Okay, so our next step to the Borel functional calculus theorem will be a little discussion of two useful locally convex topologies, namely the so-called weak measure topology, the weak measure topology, and the weak operator topology. So we suppose we have a compact Hausdorff topological space X. A compact Hausdorff topological space. We denote by B of X the algebra of bounded Borel functions. The algebra of bounded Borel functions on X. Well, actually, this is a Banach algebra with respect to the uniform norm. Moreover, this is a C-star algebra, but it's not so important at this point. And another space associated to X is M of X. We have already used this space at the previous lecture. This is the space of all complex Radon measures on X. The space of complex Radon measures on X. And this is also a Banach space. Now we define a duality between B of X and M of X by the following simple formula. So the duality will be, as usual, bilinear form. And we define it just by integration. So if f is a bounded Borel function and mu is a Radon measure, we define the pairing to be the integral of f against mu over x. And this is indeed a pairing. This is our next proposition. this bilinear form makes B of x and M of x into a dual pair. Into a dual pair of vector spaces. In other words, it is non-degenerate. The proof is a little exercise in measure theory, which is quite easy. Actually, you have to show that, in particular, that if a Radon measure mu has the property that the integral with respect to the integral of any bounded Borel function is 0, then mu is 0. And the other way around. If this is 0 for any mu, then f is 0. This is quite easy. So we get a dual pair. And let's recall now that once we have a dual pair of vector spaces, we can define weak topologies on these spaces. And now we give the following definition. The weak measure topology, the weak measure topology, WMT for short, on B of x, is the weak topology of this dual pair. In Russian we usually say слабомерная топология. We see that the weak measure topology is explicitly generated by the following family of seminorms. WMT is generated by the following family. So the seminorms are indexed by Radon measures, by complex Radon measures on X. And they are defined as follows. The seminorm is just the absolute value of the integral. The absolute value of the integral. Not to be confused with the integral of the absolute value. This is quite different. First we take the integral, and then we take the absolute value. Just as the general definition of a dual pair. First we apply the pairing, and then we take the absolute value. Okay, so we have the following simple result. I claim that the space of continuous functions, C of x, is dense in B of x. Of course, this is not correct, because if we equip B of x with the supremum norm, then C of x is a proper closed vector subspace in B of x. So it is never dense. But it is dense if we equip B of x with the weak measure topology. The proof is very easy. It is actually based on the simple part, on the easy part of the Rees-Markov-Kakutani theorem. Namely, we can consider the map from C of x to the dual, the map from M of x to the dual of C of x. Which takes a measure, mu, to the integration, the integral with respect to mu. And this map is injective. Actually, the Rees-Markov-Kakutani theorem tells us that this map is an isometric isomorphism. But at this point, we need only the injectivity. This is the easy part of the Rees-Markov-Kakutani theorem. Well, it is injective. And this implies that if we consider C of x as a subspace in B of x, and if you take the annihilator, with respect to our dual pair, then the annihilator is trivial. So this means precisely that once we have a measure mu such that the integral of any continuous function with respect to this measure is 0, the measure is necessarily 0. So this means precisely that this annihilator is trivial. But now let's recall that once we have a dual pair and the subspace of one of the spaces of the pair, then the annihilator of this subspace is trivial if and only if this subspace is weakly dense. This is our density criterion, which was proved some time ago. So this implies, by this density criterion, that C of x is dense in B of x with respect to the weak measure topology. Okay, now let's now recall that B of x is not just a vector space. Actually, this is an algebra under pointwise multiplication. So our next goal is to show that the weak measure topology is compatible with the pointwise multiplication. So we need the following definition. We define a locally convex algebra, to be an algebra. This is an algebra A equipped with a locally convex topology such that the multiplication on this algebra is separately continuous. Such that the multiplication is separately continuous. What does that mean? This means that for any element A in our algebra, the maps from the multiplication maps by A, we have two multiplication maps, the left multiplication and the right multiplication. So the first map takes B to AB, and the second one takes B to BA. They are continuous. So the multiplication on A is separately continuous in the sense that once we fix any argument, we have two arguments for the multiplication, so once we fix any argument, we get a continuous map from A to itself. At the first glance, this definition looks a little bit exotic. So it seems that it would be much more natural to require the joint continuity of the multiplication. That is, the multiplication of the respective map from A cross A to A. So the reason of giving this exotic definition is that actually there are many natural examples of locally convex algebras in which the multiplication is not continuous in the usual sense, but is separately continuous. So if we consider only locally convex algebras with jointly continuous multiplication, then we will throw away many important examples. And this is the reason why we consider only, we require only the separate continuity of the multiplication. And we define a locally convex star algebra, to be a locally convex algebra, equipped with a continuous involution. Well, clearly any Banach star algebra is a locally convex star algebra. And now we have an important example of a locally convex star algebra, which is not a bounded algebra. Namely, I claim that B of x, the algebra of bounded Borel functions, becomes a locally convex star algebra for the weak measure topology. Locally convex star algebra. To prove this result, we introduce the following important construction. For any bounded Borel function f on x, and for any Radon measure, for any complex Radon measure mu on x, we define a complex Borel measure denoted by f mu on x by the following formula. So the measure, this measure applied to Borel set B, is nothing but the integral of f against mu over B. And the general properties of the integral imply that this is indeed a sigma additive complex measure on the Borel sigma algebra. Here is a little exercise about the properties of this measure. First of all, this integral can be estimated as follows. This is less than or equal to the supremum of f multiplied by the measure of B. But here I have to replace mu by the variation of mu. And this holds for every Borel subset B of x. Well, in a special case where mu is a positive measure, of course you know this inequality. The absolute value of the integral is less than or equal to the supremum of f times the measure of B. But actually, if we replace mu by the variation of mu here, the inequality still holds for any complex measure, and this is quite easy. Actually, you just prove this first for simple functions, for linear combinations of characteristic functions, and then extend it by continuity to bounded Borel functions. And the second exercise, which is also quite easy, is that if we have two bounded Borel functions f and g, then the integral of their product fg with respect to mu is equal to the integral of g with respect to the measure f mu. Again, this is a simple exercise. It is true by definition whenever g is a characteristic function of a Borel set. Then by linearity, this is true for any simple function, that is a measurable function with finitely many values. And then, since simple functions are dense in B of x, by continuity, this formula is true for any bounded Borel function g. Okay, so now it's easy to observe that the multiplication on B of x is indeed separately continuous. So this implies that if we have two bounded Borel functions f and g, and if we calculate their semi-norm corresponding to mu, which is just the absolute value of this integral, this is just the semi-norm of g corresponding to the measure f mu. And this readily implies that the map, which takes g to fg, is continuous for the weak measure topology. Well, indeed, we know that once we have a linear operator between two locally convex spaces, and if these spaces are equipped with families, defining families of semi-norms, then we have a general continuity criterion for a linear operator between these spaces. So if we apply this criterion here, so we have to show that this is dominated by a constant multiplied by some finite maximum of finitely many continuous seminorms applied to G. But here you have an exact equality. So this is, of course, this is a seminorm from the same family, and so this map is is continuous for the weak measure topology. Well, the algebra is commutative, so actually we have to consider only a left multiplication map. To complete the proof, we have to prove the continuity of the involution. Well, the involution here is just the complex conjugation. And if we consider the complex conjugate function f bar and calculate the respective seminorm here, we easily see that this is nothing but the seminorm of f corresponding to the complex conjugate measure mu bar. And this equality readily implies that the involution is continuous. And this completes the proof. So the algebra of bounded Borel functions becomes a locally convex star algebra. By the way, the convergence of sequences in this algebra can be, for the weak measure topology, can be described in classical terms, which doesn't involve any locally convex topologies. Here's a useful exercise for you. A sequence Fn converges to F for the weak measure topology, even only if it is uniformly bounded. It is uniformly bounded and converges pointwise. I like this exercise very much because it is, on the one hand, it is rather simple, and on the other hand, it involves two great theorems from actually from different fields of mathematics, namely the Lebesgue-dominated convergence theorem and the Banach-Steinhaus theorem, the uniform boundedness principle. Well, it's natural to ask how about the joint continuity of the multiplication in this algebra. And as I claimed before, this is the genuine example of a locally convex algebra in the sense that, in general, the multiplication is not jointly continuous. The multiplication on B of x equipped with the weak measure topology is not jointly continuous. Except for the trivial case where x is finite. Unless x is finite. But on the other hand, if we look here, we easily see that this multiplication is sequentially jointly continuous. The multiplication is sequentially jointly continuous in the sense that if Fn goes to F and Gn goes to G, then Fn Gn goes to Fg. But it is not jointly continuous for the respective topologies, which in particular implies that the B of x is not metrizable. For metrizable spaces, continuity and joint continuity are equivalent. But here, this is not the case. So we have the sequential continuity of the multiplication, but it is not continuous. Okay, and let's now also introduce another useful locally convex topology. This is the so-called weak operator topology on the algebra of bounded linear operators. So suppose now that H is a Hilbert space, and we define the weak operator topology. The weak operator topology WOT for short, on B of H, to be the locally convex topology. The locally convex topology generated by the following family of seminorms. So the seminorms are indexed by pairs of vectors U and V and H. And they are defined by the following formula. If T is a bounded linear operator, then the respective seminorm of T is the absolute value of the inner product of T, U, and V. So in Russian, this is slabая операторная топология. Okay, so it turns out that once we equip B of H with the weak operator topology, we get a locally convex star algebra. B of H is a locally convex star algebra with a spectral weak operator topology. Well, let's first of all prove the continuity, the separate continuity of the multiplication. So if we take two bounded linear operators, S and T, consider their product, S, T, and calculate the respective seminorm. So what is this? This is the absolute value of the inner product of S, T, U, and V. And now we observe that this is nothing but the seminorm of S corresponding to the vectors T of U and V. And this equality shows that for any T, the map which takes S to ST is continuous. So this implies that the map which takes S to ST is continuous for the weak operator topology. Again, by the general continuity criterion for a linear operator between locally convex spaces. And to prove the continuity of the left multiplication by T, so this shows that the right multiplication by T is continuous. To prove the continuity of the left multiplication by T, let's look again here. And observe that this expression can be written in the following form. So we move S from here to here, so that it becomes S star. So this is the inner product of TU and S star V. And this is nothing but the seminorm of T corresponding to the pair of vectors U and S star V. And again, if we compare this and this, we see that the map which takes T to ST for any fixed S is continuous for the weak operator topology. And so the left multiplication is also continuous. So we have proved the separate continuity of the multiplication. Now we have to prove the continuity of the involution. And this is very easy because the seminorm of T star corresponding to the vectors U and V. So we replace here T by T star. Then we move T star from here to here. So it becomes T. And we see that this is nothing but the seminorm of T determined by the vectors V and U. So we just interchange them, V and U. And this equality implies that the involution is continuous. And so B of H is a locally convex algebra for the weak operator topology. And again, in the case where H is infinite dimensional, the multiplication is not jointly continuous. This is also an exercise for you. Okay, so now we're ready to state and prove the Borel functional calculus theorem. We are almost ready to do it, because before we prove the result, we must explain what a Borel functional calculus is. And here's the definition. So suppose that H is a Hilbert space and T is a normal operator on H. T is a normal operator, and suppose that K is a compact subset of the complex plane. As usual, we denote by T the inclusion map. Little t is the inclusion map of K into C. By definition, a Borel functional calculus for T on K is a continuous unital star homomorphism gamma from the algebra of bounded Borel functions on K to the algebra of bounded linear operators. And here, a delicate point is that we require the continuity for the weak measure topology here and for the weak operator topology here. So this is a unital star homomorphism which is continuous for these two topologies, which takes little t to our operator, such that gamma applied to little t is the operator big T. So if we compare this definition with the definition of a continuous functional calculus, we see that the essential difference here is that we use these two specific topologies. And another difference, of course, is that we defined and discussed the continuous functional calculus for arbitrary unital C-star algebras. But here we consider only one specific algebra, namely the algebra of bounded linear operators on the Hilbert space, and this is essential. Actually, if we replace here B of H by an arbitrary unital C-star algebra, then first of all, the definition makes no sense because we don't know how to define the weak operator topology on any C-star algebra. And even if we succeeded in defining this topology, we cannot guarantee the existence for the Borel functional calculus. So it's essential here that we consider only the algebra of bounded linear operators on the Hilbert space. Okay, so this is the formal definition, and here are some simple properties of the Borel functional calculus. First of all, well, let's suppose that gamma is a Borel functional calculus. A Borel functional calculus for T on K. Then, first of all, gamma is norm continuous. Gamma is continuous for the usual supremum norm on B of K and the operator norm on B of H. Why is it so? It is continuous for the simple reason that it is a unital star homomorphism from a Banach star algebra to a C-star algebra. And we have proved some time ago that any star homomorphism, any unital star homomorphism from a Banach star algebra to a C-star algebra is always continuous, and its norm is less than or equal to 1. So this is just a special case of this general result. The second observation, which follows from the first one, is that once we restrict gamma to C of k, we get a continuous functional calculus. Just by the definition of continuous functional calculus. But you know that a necessary condition for the existence of a continuous functional calculus is the following inclusion. The spectrum of T is necessarily contained in K. So we see that if this condition is not satisfied, then we have no Borel functional calculus. And finally, observation 4, if gamma exists, then it is unique. And why is it unique? It is unique because C of x is dense in here. We have proved some time ago that C of k is dense in the algebra of bounded Borel functions for the weak measure topology. And because of this density and because of the continuity of gamma, it is uniquely determined on C of k. But the continuous functional calculus is known to be unique. So the Borel functional calculus, if it exists, then it is unique. And just like in the case of the continuous functional calculus, it turns out that condition 3 is actually sufficient for the existence of the Borel functional calculus. So we have the following theorem. Theorem 1. Theorem about the Borel functional calculus. And this is our second form of the spectral theorem. Let's call it spectral theorem 2. If T is a normal operator on a Hilbert space H, a normal operator, and K is a compact subset of the complex plane containing the spectrum of T, then there exists a unique Borel functional calculus for T on K. So actually we are going to prove a more general result about extending star representations of algebras of continuous functions. Theorem 2. Suppose that X is a compact Hausdorff topological space. And suppose that I have a star representation pi of C of x on a Hilbert space H. A star representation. That is a unit of star homomorphism. Then there exists a unique continuous star representation that's denoted by pi tilde from the algebra of bounded Borel functions on X equipped with the weak measure topology to the algebra B of H equipped with the weak operator topology, such that pi tilde extends pi. Pi tilde restricted to C of k is pi. So any star representation of C of x can be uniquely extended to a star representation of B of x, which is continuous for these two topologies. So now, before we prove theorem 2, let's observe that theorem 1 is actually a special case. To prove theorem 1, we simply apply theorem 2 to the continuous functional calculus. take the continuous functional calculus for our operator T, we apply theorem 2, and what we get is precisely the Borel functional calculus. So now our task is to prove theorem 2. We'll need the following simple lemma, which is actually an exercise in general topology. Suppose we have two locally convex star algebras, A and B, and a continuous linear map phi from A to B. Continuous linear map. And suppose that phi is a star homomorphism after we're restricted to a suitable dense subalgebra. Suppose that A0 is a dense subalgebra of A, and suppose that phi restricted to A0 is a star homomorphism from A0 to B. And let's also assume that B is Hausdorff. B is Hausdorff. Then I claim that phi is actually a star homomorphism from A to B. Phi is a star homomorphism. So if a restriction of a continuous linear map to dense subalgebra is a star homomorphism, then it is a star homomorphism itself. And the proof is a standard exercise in general topology. Actually, this is everything reduces to the well-known statement that if we have a continuous map between topological spaces, such that the range is a Hausdorff space, you have two such continuous maps, and if they are the same on a dense subset, then they are the same everywhere. So if we apply this principle here, then it's easy to prove this result. Okay, so now we are ready to prove theorem 2. Proof of theorem 2. First of all, the uniqueness of pi tilde follows from the density of C of x in B of x. The uniqueness follows from the fact that C of x is dense in B of x for the weak measure topology. Let's now prove the existence of pi tilde. So we do the following trick. We take any two elements u and v in H, and we define linear functional big F corresponding to v on C of x by the following formula. This will be the inner product of pi of f applied to u and v. So clearly this is a linear functional, is linear, and bounded. Because pi is bounded. And pi is bounded because any star representation is bounded. Actually, we can evaluate the norm. The norm of FUV is the supremum of the absolute value of these numbers for over the unit ball. So u and v are fixed, and f runs over the unit ball of C of x. And since the norm of pi is less than or equal to 1, this can be estimated as the norm of u times the norm of v. Now we apply the Rees-Markov-Kakutani theorem So big F uv is a bounded linear function of C of x. So it comes from a complex Radon measure. The Markov-Kokotani theorem implies that there exists a unique complex Radon measure, mu uv, so u and v are still fixed, a unique complex Radon measure mu on x, such that fuv is the integral. The integral of f against this measure over x for any continuous function f. Let it be formula 1. For later reference, we denote it by 1. Okay, so this construction makes sense for any pair of vectors u and v. And let's also observe that the map, which takes a pair uv to the respective measure mu uv, this map is sesquilinear. This is clear because this is linear in u and antilinear in v. So now the key observation is that the right-hand side of this equality makes sense not only for continuous functions f, but actually this integral makes sense for any bounded Borel function f. So we can define, for each bounded Borel function f on x, we can now define a map phi f from h cross h to the complex numbers as follows. This will be the integral of f with respect to mu u v over x. And since this correspondence is sesquilinear, it follows that phi f is a sesquilinear form. Phi f is a sesquilinear form. Moreover, it's easy to see that it is bounded. Well, indeed, the absolute value of this number, phi f of u v, this is this integral. It is less than or equal to the supremum norm of f multiplied by the norm of the respective measure mu u v, just by the general properties of the integral. The norm of the measure is equal to the norm of this functional, because the Markov-Kokotani is an isometric correspondence. So this is equal to this one, and this is less than or equal to the norm of u times the norm of v. So as a result, we see that this can be estimated as follows. And so we see that our sesquilinear form phi f is bounded. Phi f is bounded. And now we apply our correspondence between bounded sesquilinear forms and bounded operators. So we see that there exists a unique, well, formally for each bounded Borel function, for each bounded Borel function f on x, there is a unique bounded linear operator, which will be denoted by pi tilde of f. It's a bounded linear operator on H, such that it corresponds to phi f in the following sense. So pi tilde of f applied to u, and then the inner product with v, is nothing but phi f applied to u and v, which is equal to the integral of f with respect to the measure uv. And this is formula 2. Okay, so this construction makes sense for any bounded Borel function f. So we get a map. So we have a map pi tilde from B of x, from the algebra of bounded Borel functions, to B of h, to bounded linear operators. And formula 2 easily implies that pi tilde is linear. So this is obviously linear with respect to f, but since u and v are arbitrary, this follows that pi tilde itself is linear. Pi tilde is linear. Okay, now if we compare formula 2 with formula 1, we see that pi tilde restricted to the continuous functions is nothing but pi. Formulas 1 and 2 imply that the restriction of pi tilde to C of x is pi. Probably you have you see that I'm trying to approach lemma, to approach our lemma. So to apply this lemma, we have to show that pi is continuous for the respective topologies. Well, probably I'll keep the statement here and continue here. Well, why is pi tilde continuous? We just look at formula 2 and take the absolute values of this number and this number. So the absolute number, the absolute value of this is nothing but the seminorm of the operator pi of f corresponding to the vectors u and v. Pi tilde of f corresponding to u and v. This is the absolute value of the left-hand side, and the absolute value of this integral is nothing but the seminorm of f corresponding to the measure mu uv. And this equality readily implies that pi tilde is continuous. Pi tilde is continuous for the weak measure topology on the bounded Borel functions and for the weak operator topology on the algebra of operators. Again, this follows from our general criterion, from our general continuity criterion for a linear operator between locally convex spaces. Okay, so now we are precisely in this situation. So we have two locally convex algebras: the algebra of bounded Borel functions, the algebra of bounded linear operators equipped with the respective topologies. We have the dense subalgebra of continuous functions, A0. We have this property, so the restriction of pi tilde to the continuous functions is pi, but pi is a star morphism. Clearly everything is Hausdorff. And so we conclude that pi tilde, we apply our lemma, and we conclude that pi tilde is a star homomorphism. And this completes the proof. So pi tilde has all acquired properties. It is a continuous star representation of this algebra, and it extends pi. So this completes the proof of theorem 2. And as we have already observed, theorem 2 implies theorem 1, that is the existence of Borel functional calculus. Okay, so that's all for today. And the next lecture, and most probably the next lecture will be the last one, we will prove another form of spectral theorem, which gives a useful integral representation for a bounded normal operator in terms of some projection valued measure, the so-called spectral measure of an operator. So in some sense, this gives us an approximation of normal operator by linear combinations of projections, which is also quite useful. And moreover, we will see that this is, in a sense, canonical. So we get a one-to-one. We will get a one-to-one correspondence between normal operators and so-called spectral measures, which are measures with values in the set of all projections on the Hilbert space. And if we have time, we will probably discuss some applications of this spectral theorem. Thank you.